density estimation material. Any questions before we get started? Okay, let's just quickly remind ourselves. We've got a sample for density. The risk we've been using has been the integrated squared error. We did the histogram analysis on last week. And we saw that the risk there was, what was the bias? It was like bias squared was like, I guess, h squared, order h squared. And the variance was of order 1 over nh to the v. And minimizing over h, that gave us something of order 1 over n. Correct me if I'm wrong, that's my memory here. And that was the histogram analysis, right? Okay, and then we just started to talk about the kernel density estimators, which will look something like this in v dimensions. I'm using, again, a same bandwidth in each direction, which is a special case, and that looked like this. And that was the kernel density estimator with the bandwidth h, which controls the smoothing. And so what we're about to do was compute the bias and variance of this thing and see what the optimal bandwidth is. So I think that's where we left off. Okay. Any questions? So let's first of all, so on the notes here, on the density estimation notes, we're on page 6, or actually I guess page 7. Let's start with the one-dimensional analysis. I think when you go to compute the bias and variance of this, if you haven't done it before, it looks a little bit intimidating. It's a complicated expression, but when you think about it, it's an average. Just call this thing yi. Let's focus on one particular point x. And so this is really just an average, 1 over n, let's say yi. And so when you think of it that way, computing the mean and variance is not so bad. Computing the mean, what's the mean of an average? The mean of an average is the expected value. These are IID, so the mean is just the expected value of any one of them, right? The expected value of x bar is just the expected value of x1, or x2, or x3. So all I need to do is take the expected value of one of these guys. I'm going to do this in one dimension for the moment. So just take d to be 1. Everybody with me? This is just one term. I could put xi here, but it's called x linear. So all that's random is this. That's the random variable. Is that good? And to compute the expected value of this, I just integrate. So this is random. So the expected value is the integral. This is 1 over h. Now here's the trick we always use to do these things, so this is a good trick to know, which is just to do a change of variables. So let's get rid of the u minus x over h here and call that t. And then when you do the Jacobian, you get a h which kills this. So this becomes k of t e of x plus tu, sorry, t h dt. Everybody with me? So I just did change variables. Why did I know to do that? Because it turns out this is actually now a pretty helpful thing to have, because now we can take advantages of the properties of P. Remember, to do density estimation, we had to assume some properties about P. And so when I see a term like this, and I think of the bandwidth as being small, and we're trying to estimate, remember, P of x. And you can see there's a p of x here except for this, so that suggests, it's just crying out for you to do a Taylor series approximation. So what we want to do is write p of x is t of h is p of x plus th prime of x plus t squared h squared over 2 and double prime of x and so on. So if I plug that in here for this, I'm just going to go to second order. So I'm going to get 3 integrals for each of those 3 terms. So the first term I'm going to get P8, I'm going to get P of x. So this is going to become, I'm continuing this here now. This is P of x. That's the first term. Well, what's the integral of k of t dt? I'm left with the integral of k of t dt. 1. That's why we chose the kernel to have integral 1. So I have the integral of k of t dt. Now the next term looks like this. T, that's the second term. But remember, at some point when I said the kernel has to have very few properties, it's got to integrate to 1. The other property I said is it has to be symmetric. It has to be mean 0. Because that makes that 0. That kills that term. This is what's going to make it have a faster rate than the histogram. That, instead of having a bias of order h, the order h term is now dead. And then the last term is t squared h squared 2, oops, squared plus small order terms. Let's say plus terms of smaller order h squared. But look at this. This is a constant, right? That's just like the variance of the kernel. That's just some number. So we actually have a pretty simple thing here. We just took the mean of the kernel density estimated at a particular point P, and we see it's equal to the truth plus something, so that's the bias. The bias, remember, is the difference between the expected value and the truth. So what we've just shown is that the bias is some constant times h squared plus smaller order terms. Notice why I said you have to make assumptions here. If p double prime didn't exist, this whole thing wouldn't have made sense. So we're assuming that the second derivative exists for this analysis. We're assuming a certain amount of smoothness. Okay, any questions about the bias calculation? Now when you do the variance, I'm not going to go through it because it's very similar. The variance of an average is the variance of any one of them divided by n. And then you do a change of variables, and so it's a similar kind of a calculation. You can go through that, and you'll see that the variance is basically equal to something of order 1 over n h plus small order. In fact, here's an interesting thing. If I had done this in d dimensions and still assumed twice differentiability and done the same analysis, the bias doesn't change. The only thing that changes is the variance. So more generally, in RD, you would get that the bias is again of order h squared. The variance is what changes. It's of order 1 over n h to the d. And so what we get is that the risk is of order bias squared. So when I write twiddles like that, I mean there's constants I'm leaving out, right? Bias squared plus the variance. And again, if we wanted to, we could say plus little o in terms of small order and so on if we were being rigorous. That's showing you what's going on with kernel density estimators. That's, you see the bias increasing with h and the variance going up as h gets small. And again, we could ask, what's the best h? Which h minimizes this? It's going to be of order some constant over n to the 1 over 4 plus d. And if I plug that back in, the risk is going to be of order, let's say, of order 1 over n to the 4 over 4 plus d. This is assuming twice differentiability. In a few minutes, we'll do a little bit more general analysis. The 4 will be replaced by something else. This is the most common assumption. So what we see is that if I can pick the best possible bandwidth, and if I assume that the density is twice differentiable, the kernel density estimator has a risk which is going to 0, like 1 over n to the 4 over 4 plus d. That's faster than the histogram. But we're also making slightly stronger assumptions. For the histogram analysis, we only assume that the density was Lipschitz. Here we're assuming that there's 2 derivatives. So we're assuming a bit more, but in return we're getting a faster rate. In particular, in one dimension, we get 1 over n to the 4/5. So on page 8 and 9, there's an analysis. I repeat the analysis. I don't think I'm going to go through it because it's just details. You should go through it. But it repeats the analysis under more general assumptions. The more general assumption is basically that instead of assuming there's 2 derivatives, what if you assume there's beta derivatives? Beta is some number. In the notes, beta is actually allowed to be a real number. Just take it to be an integer. So a common assumption is that there's 2 derivatives, beta is equal to 2. But if, again, we can do it with 3 derivatives, 4 derivatives. If you make more and more smoothness assumptions, you'd expect to get a better and better rate. What ends up happening on page 8 and 9 is the analysis is not actually that much more complicated than what we just did. You'll see that the thing to keep in mind is this. Adding more assumptions like smoothness doesn't change the variance, it changes the bias. What ends up happening is the bias becomes of order h to the beta. And what we did was a special case with beta equals to 2. And the variance is 1 over n h to the d again. Other than that, everything's pretty much the same. All that happens when you assume more smoothness is did you see how I did this Taylor expansion and killed off the first term? If you assume more smoothness, you can keep going out more and more terms and kill off more and more terms, although you have to pick the kernel carefully to make sure you're killing off all those extra terms. But you can only go out as far as however many derivatives you're assuming. And what that buys you again is that you get rid of more and more terms, so the bias becomes h to the beta. The final rate becomes of order 1 over n, 2 beta plus d. So this is an expression you will see a lot. Whenever you're doing non-parametric analysis, many, many different things turn out to have a rate of the form 2 beta over 2 beta plus d. Why? Well, they're all different versions of the analysis we just did. You compute the bias, you compute the variance, you optimize over some tuning parameter, and you find that the rate of convergence looks like this. So again, the most common assumption would be minus 2, which would be 4 over 4 plus d. But in principle, you know, if you had more smoothness, you'd have a faster rate. What happens, in fact, when beta goes to infinity? Suppose I let beta go to infinity. What would that rate be?
It approaches the parametric rate.
Right, it would go to 1 over n, which is what we're used to getting for parametric things, right? Like how far is x bar from mu? The mean squared error is like 1 over n, which is parametric. That's like an parametric problem. So you can think of, as I add more and more smoothness, I go from non-parametric to parametric. That's like a bridge from non-parametric to parametric. So, again, in reality, we usually use beta equals to 2, but to keep the theory general, people usually express it more generally like this. It's unusual to say, oh, I'm going to assume there's 3 derivatives or 7 derivatives or something like that. But it's good to have the general theory. And in fact, again, just like in the Instagram case, we can ask, well, if I assume there are beta derivatives, can I do any better? And later in the course when we do minimax theory, we'll see the answer is no. So this is now on page 10. You'll see that if I take the infima over all possible density estimators, and if I take the suit over this class of densities, and what this class is described in the notes, but for our purposes, just think of it as the set of things with beta derivatives. And if I look at the expected value, okay, so this is the minimax analysis again. You give me an estimator, p hat, and I take any density p in the class and compute its risk, and now I ask, what's the worst case risk, the suit? And now I say, what if I were to minimize it over all possible density estimators that exist? We would see that it's bigger than some constant, some universal constant. So at least up to rates, you can't do better than kernel density estimation. There are actually lots of pragmatic, practical reasons for sometimes doing things other than kernel density estimators. So whenever I say that kind of optimality result, again, don't think that, okay, therefore I should never think about any other estimator. There's all kinds of practical reasons why you might want to use other estimators. But at the level of the theory we're talking about here, in terms of the minimax rate of convergence, we know that kernel density estimators achieve this rate, and that's the best you can do. So it's an optimality property of things. Brian, were you going to?
I just wanted to ask, or maybe point out that even aside from the practical considerations for kernel density estimates, there is still a theoretical interest outside of them if we don't assume that our density lives in that class, right? It's only minimax over that class.
It's only minimax.
Took a broader class of functions that would. So.
Right. So when I say it's minimax, it's relative to this assumption. If you pick a different function class, and there are other function classes, it will no longer be the minimax estimator necessarily. Right. All right, so we still haven't got to the practical question of how am I going to pick this bandwidth in practice. That probably should have been next. For some reason, I put the confidence bands next. Let's stick to the notes. I'll do the confidence bands. So the confidence bands, the easiest way to talk about this is I'm going to use a technique that we're not actually going to explain until later in the course. So right now it's going to be an algorithm. It's going to seem magical, but we'll show you later in the course why it works. All right? And what is it I'm trying to accomplish here? Well, if you look at page 11, what I've got here is the top left shows you some data that I generated. Okay, so you can see there's 2 bumps of data there. Right? And what I'm showing you is the kernel density estimator for different bandwidths. There's h equals to 1, h equals to 2, h equals to 3. Again, in about 10 minutes, we're going to talk about how in practice you pick h, but let's not worry about that yet. But what you're also seeing there are confidence bands. Whenever we estimate something, we'd like to have some notion of uncertainty for it. And these are 95% confidence bands, and I want to show you how I constructed them. So first I want to take a minute to explain what I mean by confidence band. Remember back in parametric inference, what was a confidence interval? If you were estimating a parameter theta, like the mean of a distribution, you would have some sort of estimator. You learned about the 705, like the MLE or the method of moments estimator. And you also learned about confidence intervals. What was a confidence interval? It was some sort of interval, let's say C. And there's a lot of stuff hidden here, right? Because these endpoints are actually functions of the data. It's a random interval. And you chose that in 705 to track the true value, let's say 95% of the time, or whatever. right? So you chose this confidence interval, you constructed it so that the random interval tracked theta with probability at least, let's say, 1 minus tau. Remember that theta is fixed, it's the procedure that's random, right? So you did this in 705, I know you did. All right. So we want to do a similar thing for the function. We're trying to estimate a function. And there's actually two complications. Here's the function. I'd like to put a band. So it's not a parameter, it's not a number, it's a function. I want to put a little band around it. So one complication is I need an upper and lower function. It's not just a confidence interval, but actually two functions. But there's another kind of subtle problem that comes up all the time in non-parametric inference, which is known as the bias problem, which is, in some sense, it's impossible really to come up with a confidence interval for something like a density function. And we're gonna make a weaker statement. So let me tell you what I'm talking about here. Let's look at our kernel density estimator. Here's our kernel density estimator evaluated. Let's just worry about one point for the moment. Let's just fix a point x. Okay. And I want to compare that. Let's see, how did you construct confidence intervals in 705? You, see if I can find a chalk brush first of all. Everybody's pointing is right in front of them. Thank you. You probably did something like this. And you said, well, here's my estimator, here's the quantity of interest, and then you had some sort of standard error, right? Some sort of approximate standard deviation. And you probably said, well, this approaches a normal distribution, and you got a confidence. Does this ring a bell? Coming back? Yeah. Okay. So we might try to do the same thing here. We could say, well, I'm interested in density, and then I'm going to somehow estimate the standard deviation of this thing, which actually turns out to be fairly easy to do. Let's call that this. But here comes the subtle problem. Remember that we just worked out that p hat had some mean. So when we did the bias calculation, we computed the expected value of this thing. Let's give that a name. Let's call that P. So that's the mean of the density estimator. Density estimators are not unbiased. So, in fact, we worked out the bias. The bias was of order 8 squared, or whatever it was. Right? So there's some bias here, which means this is not equal to P. In fact, if you were to plot this, what it looks like is a kind of smoothed out version of P. So if this is the true density, imagine I gave you data from that density and you computed the kernel density estimator. And imagine doing that many, many, many times and averaging the estimator. That's what you get, right? So that's what the expected value is. What it would look like is this. It's kind of a smudged out version of the true density. It's a smoothed out version. That's not surprising because that's what we're doing when we're doing kernel density estimating. We're smoothing. So it's kind of a smooth version of the truth. So what I want to do here is add and subtract the mean. Okay, so again, I'm trying to mimic what you did in 705. I want to take theta hat minus theta over its standard error. So I'm taking the estimator minus the truth over the standard deviation. I added and subtracted the mean. Okay, now it turns out this part is no problem. This actually does obey a kind of central limit here. And so from that, one can create methods to get confidence sets, which we'll talk about in a second. The complication is this. What is pH of x minus p of x? What is that? This is the mean of the estimator minus the truth. That's the bias. And this is the square root of the variance. But what was the optimal H? The optimal H was precisely the H that balanced the bias and the variance. When we minimized over H, we had a bias term and a variance term, and we couldn't let either one dominate. The optimal value of H was precisely the value of H which balances the bias and the variance. That's what it means to find the optimal bandwidth. So if you imagine that as you're getting more and more data, you are always finding, let's imagine the best possible world. You're finding the best possible balance. You're balancing the bias and the variance. This and this are always going to be about the same order. This is never going to go to zero. So what's going to happen is this is going to converge to a normal plus a constant. This is something that didn't happen in parametric inference. In other words, if I construct a confidence interval, it's not going to be centered at the true density. It's going to be centered around the mean of the estimator. Whoops, there's something missing. Oh no, that's yeah. Okay, the confidence interval is going to be centered around not around the true density, but around this mean function. The reason why no one told you about this in 705 is because in 705 we could have done the same thing. They could have said, well, you know what? We should really subtract the mean of the estimator here. And really your central limit theorem applies to this, but how about this extra term? But in parametric inference, the bias is much smaller order than the variance. So this term is actually in parametric inference, it doesn't even affect anything. That's the difference between parametric and non-parametric inference. So what does all this mean? All this means is this. When we construct a confidence band that I'm about to show you, it's not going to really be centered around the true density. It's going to be a little bit biased. It's not, in my opinion, it's not a big issue in practice. You just have to be aware of the problem. Technically, we're making a confidence band for this function, not the true density. And it's kind of a small technical point, but it's conceptually it's kind of important. And so there's the algorithm for doing it. I'm just going to explain it. It's a type of bootstrap algorithm, it's called. And then again later in the course we'll have a lecture on the bootstrap and we'll show you why this works. But the algorithm is very simple. Here's the algorithm I used to make those pictures. So I have data, remember, and I constructed, step one was I constructed the density estimator. Should call it that because there's a bandwidth. Now, step two is, well, I need some notation first of all. Called the empirical distribution, which just means the distribution which puts mass 1 over n at each data point. So if this is x1, x2, x3, x4, whatever, and you just put mass. And just think if that's some distribution, right? It's a discrete distribution, but it's a well-defined distribution. It happens to be discrete. It puts mass 1 over n at each observed data point. You can also think about it as a table. So here's x1, x2 down to xn. And each of these points gets mass 1 over n. This is just some distribution. We're going to keep the observed data fixed. And now what you do is you draw, step two is you draw what's called a bootstrap sample, which means I draw n data points from this empirical distribution. So let's think about what this means. It means I take this distribution and I draw an observation. It's pretty easy to draw from a discrete distribution. Now I draw a second independent one, third, fourth, until I get n of them. Or equivalently, I look at this table and I draw one of these points with equal probability. I record that point. And now I repeat n times. That's all I'm doing. So these n data points are drawn from this empirical distribution. Is that clear? Any questions about what I'm doing there? Am I going to get back? Is this going to be the same as the original data set? No, because I'm drawing independently, so I might get ties or repeats. Now I compute a new kernel density estimator using this bootstrap sample. So let's call that star of x. Okay, so I just pretend this is the data now. And I plug it into my R function to compute my kernel density estimator. And I compare it to the original estimator. So now I can look at the original estimator. And I take the largest of all x's. Did I give this a name? Somewhere I gave it a name. I think I called it R. Did I call it R?
Yes.
Okay, so actually in the notes, I also did the following thing, which might seem kind of strange, but I multiplied this by n h to the d. This is not actually necessary in the algorithm. You'll see in the theory why we do it. I'm going to end up dividing by this later anyway, but let's do it. Okay, so I take the maximum and I do this. Is that clear? Okay. That's once. Now I repeat this 10,000 times. When I say repeat it, I mean repeat the whole process. I draw a bootstrap sample, I compute the new estimator, I compute how far it is from the original estimator, and I get a number, R. So let's call these numbers now R1, R2, R, say capital B. Think of capital B as 10,000. Make it as big as you want. And now all I do is I find, so here's those numbers. We have 10,000 numbers. I'm going to find the alpha quantile. So alpha here is the confidence level, like 0.05. And I'm going to find the point here, let's say Z alpha, which has 5% of them to the right. So that's just the upper quantile. And now we're done. The confidence band is at x of h plus or minus. So notice I never really needed to multiply by nh to the d because I'm going to divide through by it. But when we do the theory, you'll see why it's better to define it that way. Okay, so you draw a bootstrap sample, get the distance, repeat 10,000 times, get the quantile, and that gives you the band. That's how I got those bands. That's called the bootstrap confidence band. And officially what the property is, is that, let's call the lower band L and the upper band U. Remember, it doesn't really track P, it tracks the mean of the estimator, which you can think of as approximately equal to P. And the property that this has is the probability that we track this guy for all x. This is actually an asymptotic statement, so it's the limit as n goes to infinity. Bigger than 1%. The importance of doing this in practice is that computing an estimate is fine, but you always want to have some idea, right, of how uncertain your estimate is. So it's a good idea to put some sort of standard error or confidence interval or something around whatever you're computing, so you get an idea how much variability there is. And that's exactly how I computed those pictures. And you'll notice that, let me find the picture. Of course, the shape of the band, the shape of the estimator and the band changes drastically depending on h. So we still haven't talked about how to pick h. I'm just doing this for different h's at this point. But now you know how I computed the estimator, and you know how I computed the confidence span around this. If you've never seen the bootstrap before, this is kind of mysterious that this actually works, but again, we'll talk about this theory later. Yes?
Going back to something that you said earlier, that the estimate converges to a normal distribution plus an offset. So would it make sense to choose it in such a way that the bias is less than the variance?
So there is a school of thought that says, let's choose H smaller than the optimal bandwidth, which is called undersmoothing, and it gets rid of the bias. The problem with that is, now you have, it's going to be hard enough to choose the optimal bandwidth. Now we need some optimal way of choosing a suboptimal bandwidth. And how suboptimal should we pick it? And it's a very murky area, and I'm not sure in practice people really do that, although there's a lot of theoretical papers about that.
Does this confidence interval become a real confidence interval for the true distribution if we make some parametric assumption?
Well, yes. If we did parametric inference, there wouldn't be any problem. It's all because we're doing non-parametric inference.
But it's like for each bandwidth size, is there some parametric assumption that would make it real?
That would be a difficult thing to play. We would end up in kind of a infinite loop to try to do something like that. Yes?
Do we expect any sort of distribution for R, values of R we are getting with bootstrap?
Yes, so what is the distribution of R? It has a known distribution. It converges to something called a Gumbel distribution. It's some weird distribution. That's probably not that helpful. It's just some weird distribution. Yeah.
So what's the distance function you're using between the bootstrap density estimator?
It's the soup distance, the maximum distance. And the reason is I want to make sure that this is holding for all x simultaneously. Yes?
There'll be some parts of your sample space where you have a lot more data and you're more certain of the density estimate. So can you do better by narrowing the interval there?
Yes. So what you can do is instead of looking at this minus this to super this, you could do what's called studentizing it, which is dividing through by its standard deviation. And you do get variable with things. Is Fabrizio here? I think Fabrizio can testify to the fact that in practice, it doesn't actually seem to make much difference, but in principle, you can do that. Okay. Good. So that was a little taste of the bootstrap. Let's turn now to the very important practical problem. How do we actually choose the bandwidth in practice? So you've done this kind of thing with classification where you have to take some sort of tuning parameter and you know we're going to do some sort of cross-validation. The theoretical stuff we did was useful for saying the optimal bandwidth is of a certain order, but I kept leaving out constants everywhere. So you can't really use that theory to help you pick the bandwidth in practice because there's all these constants floating around. The constants depend on the true density, and we don't know the true density. So that's why we resort to things like cross-validation. And as you know, there's many flavors of cross-validation, so let's talk about two of them. Also, cross-validation and density estimation means something a little bit different than it does in classification because there's no label we're predicting. Right? In classification, we use cross-validation to predict labels. There's no labels here. This is unsupervised. So what do we even mean by cross-validation? So there's more than one way to do it. But typically, we look at it like this. We say, all right, let's go back to the loss function. Ultimately, we've been using this L2 loss. Somehow what we want to do is make this small, right? That's really our goal in some sense. And so let's expand the square. So I just expanded the square. What I'd like to do is somehow find a way to pick the bandwidth h to make this quantity small. Well, the first thing to notice is look at this term. There's no h there. So when I go to minimize over h, this term doesn't matter. So I'm just going to ignore that term. We don't care about that. The first term, we know this. This is the estimator we just computed. We can square it and integrate it. We're almost done. There's only one catch. The second term has the true density in it. Now, if we weren't careful, we might say, oh, no problem. This is an integral with respect to p. That's an expected value. I'll just take the average, sample average. Right? When if I gave you a function of this form, if I said compute this integral, and you said, oh, I don't know p, but I have sample from p, you'd say, well, we learned in 705, law of large numbers, this is approximately 1 over n. You just take the average, right? That's a disaster if we do that here. Why? Well, yeah, but even more than that. I mean, the data are at
The h hat is already estimated.
So yeah, this is a random function which has already used the data. This is not a fixed function g. If we double use the data to estimate the risk and the estimator, you're going to end up getting h equals to 0. Okay? It's the usual problem that when you estimate the risk, you can't use the same data to estimate the risk, just like a prediction, the risk, as you did to come up with the estimator. So what we do is some sort of leave something out idea, and the easiest one is leave one out. So what we'll do is we'll leave one out, cross-validation estimator. This is equation 20. Actually, for some reason I left it out in the first. You don't really need to do that. So I should really just say this. The first term we know. It's the second term that's a problem. So we're going to do what we wanted to do, which is put the average here. But to avoid this bias problem, what we're going to do is we're going to make sure that when I plug in the ith observation, that I leave the ith observation out. Okay? So in other words, you take each observation, you leave it out, you find the density estimator, which is a function, you evaluate that function at xi. And you should convince yourself that you take the expected value, this will be now an unbiased estimate of the risk. This is the leave one out estimate. And that is something we can compute from the data. So if you plot this, you'll get hopefully some nice thing like this, and you'll just minimize this. I actually wrote down in equations 21 and 22, in the special case when we're using a normal kernel, you can write out more explicitly what all these integrals, you can do the normal integrals and all that stuff. So you get some sort of messy expression, but it's not too bad. So there's a bit of work to do here, because you have to do the integral and all that stuff. But in principle, it's very simple. And so it's leave one out cross-validation, although again, there's no label. We're using the leave one out idea, though, to get rid of the bias of using the same data to compute the estimator and estimating its risk. However, that's not the only way to do cross-validation. You also did in 701 things like tenfold cross validation. Those ideas can also be used here if you want. So you would split the data up into pieces and leave out a chunk of the data and estimate the risk with the left out chunk and repeat it for each chunk and average, just like when you're doing prediction. The only difference is the quantity you're estimating is this. So what you'd be computing each time is the integral of p hat squared minus 2 over n, where this is now the sum over whatever the held out data are. So you can do leave one out, you can do splitting it into 2, splitting it into 10, there's many different flavors, just like there are for doing classification. I think in density estimation, the most common one is leave one out, but you don't have to do it that way. So now we actually, yes, question?
In case of cost validation, which is a better idea, leave one out or split it?
Well, that's a very good question. So what's better? Is it leave one out, splitting it into 2, splitting it into 10? I can tell you this, in terms of theory, in fact, section 4.2 has a very precise theorem, which I wasn't going to go through, but it's there for you to read it now, which shows you that if you do data splitting and you optimize the bandwidth from the second half of the data, the resulting density estimator is very close to optimal. I don't know of a similar theorem for leave one out cross validation. Maybe it exists and I'm just not aware of it. There's kind of another second order bias variance trade-off here, because leaving one out has very low bias. You're changing the sample size from n to n minus 1, but they're very correlated, all the estimates, so you have a high variance. When you do data splitting, you get a much lower variance, but now you're really estimating the risk of n over 2 instead of n, so it's kind of a bias. And you could kind of try to say, well, is there an optimal way to split it and so on, but I think it gets, you could probably do theorems about it, but I don't know how practical it would be. But if I had to guess, I would say for density estimation, most people probably use leave one out. I don't know. See if the guys at the back here, they're not objecting, so I'll take that as a good. Okay, so now what we have, we're almost done here, is we have a pretty complete theory in the sense that we have a loss function, we have a method, kernel density estimation, actually we have other methods too. We can compute an upper bound on the risk, and we can also say that that bound is up to the rate, the minimax risk, so you can't do any better under those particular assumptions. And we have a practical method for picking the bandwidth and for getting a confidence band. So it's a fairly complete story. There's a couple more points I want to mention, and then we're going on to, Ryan's going to do Gregory not dimension regression. But let me just mention a couple of other things. This gets hard in high dimensions, okay? So we can see that in the rates. The d in the exponent is, kind of a painful thing. That's the curse of dimensionality. If I ask you, suppose I want the mean squared error to be some small number, epsilon, and solve for n. How big does n have to be? You can see that n has to increase exponentially with the dimension. And that's because as the dimension gets bigger, the data get more and more sparse. There's very little data. Once you get to 5 dimensions, every data point is almost an isolated point. So you need a lot of data at high dimensions, at least the way we've done this, to do density estimation, or for that matter, any non-parametric thing. And computing also gets harder, right? Computing anything in higher dimensions is more difficult. But that's not as big a problem in some sense because, I know lots of smart computer scientists and they figure out fast ways to compute things, so I just ask them how to compute it. But the statistical cursive dimensionality, it doesn't matter how smart you are, it's kind of like a fundamental limit on, in terms of how much information there is, that there's no getting around it in some sense. Now there are some things you can do in high dimensions if you're willing to live with more bias. So the simplest one would be what's sometimes called, or plays a part in the naive Bayes assumption. Suppose you had a high dimensional density, and D was really big. You might say, look, trying to estimate the density really accurately is hopeless. Let me try something that's easier to do, a little bit more biased. And the naive Bayes assumption is, let's pretend all the coordinates are independent. So let's act as if the density is equal to the product. That's going to introduce some bias, because certainly the true density isn't going to be completely independent like that. But at least you get out some estimator. And now what you've done is you've reduced this to what? To just estimating a bunch of one-dimensional densities. So under the naive Bayes assumption, you can just say P hat of X is just the product. Okay, and you're making a compromise there, right? You're trying to do something easier. But of course, you have to bear in mind that you are introducing some extra error. In fact, later in the course, we'll talk about the dimensions. There's lots of other things you can do to try to reduce the dimension first before doing density estimation and so on. But a lot of this will depend on what it is you're going to use the density estimator for. So anyway, just keep in mind that, like all things, once you get to high dimensions, things get much more difficult. All right. I want to conclude by just briefly mentioning one other method. Oh, a little example of, just a small example. On page 17. I just wanted to show you a simple data set in 2 dimensions. I use 2 dimensions because I can draw in 3 dimensions. So there's a very simple 2-dimensional data set. It looks like a ring. I made it a ring because I wanted to pick something where clearly using like a normal or some parametric family wouldn't make much sense. And what you see there is actually the plot of the estimated risk, cross-validation. So that is the cross-validation error. I've computed a 2-dimensional kernel estimator for each bandwidth, and I'm plotting the estimated risk as a function of bandwidth. And then what I do is I choose the bandwidth h that minimizes that, and the resulting density estimator I've drawn as kind of a heat map or something on the bottom left there to show you the density. It comes out kind of lumpy. It's a little bit hard. Maybe I should have done actually a perspective plot that would be easier to look at. But if I had drawn this better, you would have seen like a bumpy kind of density involving the ring, kind of what you'd expect. And just for comparison, I also tried increasing the bandwidth. It's kind of hard to see here, but of course, as you increase the bandwidth, you get a smoother estimate and so on. Nothing surprising going on there. I just wanted to show you what a simple example is. Lastly, I wanted to really briefly mention a different approach, because I didn't want to leave you with the impression that kernel density estimation is the only way to do density estimation. It's probably the most common one, but there are a zillion different ways of doing density estimation. So I thought I would mention just one other one, briefly, which is using series methods. So suppose, again, we have some data. We want to estimate a density, and to keep things simple, I explained this on page 16, just assuming that we're on the unit interval, although there's nothing special about unit interval or one dimension. This is just to keep it easy. And the idea of the series approach is the following. Let's assume that, first of all, we're going to assume that the integral of p squared is finite, which is actually a fairly weak assumption. And then if you remember your Fourier analysis, what does that mean? It means you can expand P in some sort of orthonormal basis. So what's an orthonormal basis? Let's remind ourselves. We're going to take a sequence of functions. So it's an infinite sequence of functions. Each one has the property that when you square it, it integrates to 1. And any pair of them, they integrate to 0. So think about sines and cosines. Actually, typically you would take the first one to be the one function. So the first function is probably going to look like this. 1. Then you might have like a cosine, and then a higher frequency cosine, and a higher frequency cosine, something like that. Your typical, there could be Legendre polynomials. I'm sure you've seen lots of families of orthonormal functions before. Think of them as becoming more and more and more wiggly. And what do we know from when you took calculus? Well, you know that I can always write any density P as a linear combination of these basis functions. Remember, the basis functions, we know they're known functions. So I can write P as a linear combination The only thing we don't know are what? The coefficients. But we know that there's a formula that, again, in calculus, you learned that what is beta j? It's the inner product between P and the basis function. I hope this is all familiar. Right, remember this? So I take a P, I can write it as a linear combination of basis functions. The coefficients, we don't know them, but they have this form. It's the inner product of the jth basis function with the function itself. Of course, this presents a problem because we don't know P. But you can see immediately, well, I don't know P, but I have a sample. So there's a very obvious way to estimate that, which is beta j hat, which is going to be the average of this. Because if I take the expected value of this, I get precisely back beta j. And we're almost done, because now if I look at P, all I have to do is stick in those beta hats. Except for one thing. Do you see any problem if I just insert it into this series? Yeah, we're trying to estimate infinitely many parameters and finite number of data. If you compute the variance of that thing, it's going to be infinite. It's like letting the bandwidth go to 0 in kernel density estimation. So in series estimation, typically what you do is you truncate it, and that truncation parameter is just like the bandwidth. You can now do all the same stuff we just did. There's a bias variance trade-off. You can make K too big, you get too much variance. If you make it too small, you get the bias. You can write out the bias and the variance. In fact, analysis is actually somewhat easier for series estimations. You can do cross-validation for finding the optimal K. So the whole story we just did can be done exactly with series estimators as well. They're probably less used maybe than kernel density estimators, although I guess it's a matter of personal preference. There is a certain amount of art to choosing a good basis, just like there is in choosing a kernel. So I told you the choice of kernel doesn't matter much, and for most problems that's true. And the same is true here. The choice of series, for most problems, doesn't matter much. But if you're doing something really delicate like signal processing, where you might have sharp peaks in signals and things like that, then people are very careful about what orthonormal functions they might use. They might use something like, some of you may have heard of wavelets. So a wavelet basis is a particular orthonormal basis that's good at certain tasks and so on. So it can become a whole art trying to choose the basis properly and so on. Okay. So we don't want to go into series estimation in detail. I will tell you though that under the standard, under reasonable assumptions about the density, which are now expressed in terms of the beta j's. So the smoothness conditions on P now become conditions on the beta j's dying off quickly enough. And you get exactly the same rates. You get rates of 1 over n in general like this, where beta is measured in terms of smoothness of the density and so on. So although the theories and the methods start out looking very different, the final estimators and the results and everything end up looking very similar actually. So there are different paths and so on, but in many ways they're very similar. Okay, another thing I wanted to briefly mention is, I've been talking about using one bandwidth. It may have occurred to you that maybe you want to use different bandwidths in different parts of the space. That's called variable bandwidth estimation. I think Ryan will talk a little bit about that, right, when he does regression. It's hard to do. You need a lot of data to do that. It's hard to pick one bandwidth well. If you're going to pick a lot of different bandwidths, generally you need a lot of data to it. But there are certain applications where that turns out to be important. But we kept things simple and just assumed single. All right, and lastly, I want to tell you that there's optional information that's in the appendix. It's not required, but if you're really excited, if I've gotten so excited about stuff, you just need to read more. There's some concentration and measure analysis for histograms and kernels in the appendix. There's also a section about L1 methods. What if I had used L1 instead of L2 as a loss function? So you'll see there's something in the appendix about that. If you want to see that, you're welcome to look at it. But again, if you're not that interested in it, then you can skip the appendix and read it some other day. Right? So that pretty much covers everything we want to do for now, at least for density estimation. Let's pause and see if there's any questions.
Maybe it's a previous question, like, say, we do graphical models and we do mixture of Gaussians. Similarly, we could have done a mixture of exponentials and expectation maximization. Is that a feasible?
Yeah, so let me generalize your question a bit. Another way that I didn't talk about for estimating densities is to use mixtures of normals. Right? So why? And my plan was to actually talk about that in a little bit of detail later in the course. Mixtures are really interesting things. They're much harder to deal with numerically and much harder to analyze. They're still not understood. In fact, the asymptoticity of mixtures is still pretty much unknown for a lot of things. But on the other hand, they are quite popular and people like using them for certain things. So I can't remember if we put it on the schedule or not. I have a section of notes all about mixtures, and I was hoping to defer that to later in the course. So hopefully we'll squeeze that into something because there are some interesting issues. But that is another approach to estimating densities. You use a mixture of normals, k normals, and treat k itself as a parameter which can change. So you can make it richer and richer as you let k get bigger and bigger. So that is another approach to non-parametric densities.
Sometimes graphical models.
Well, I'm not sure I would say, I mean, graphical models, undirected graphical models can do that.
Like, you have peaks and you assume Gaussians there.
Okay, I'm not getting the connection. That's more like clustering to me rather than graphical model. So we will talk about density-based clustering methods, yes. Later in the course, yeah. That's sort of a non-parametric version of clustering. In fact, we'll talk, so that's actually a good place where we'll compare mixtures of normals versus kernel density estimation for clustering. That's a good place to compare them, in fact. Anything else? In that case, Ryan, is Ryan ready? Yeah, Ryan's going to take over. Start. Non-parametric regression. Don't forget, by the way, homework is due Friday.
Keep my time zone.
I want to meet my,
Yeah, because there's
please hit this.
All right, so I guess we only have maybe 15 minutes, so I think I'll probably just set us up for non-parametric regression, and the next week we'll kind of hit the ground running. We're going to try to cover a good number of methods, and we're going to try to focus on, so there is obviously an analog to kernel density estimation in non-parametric regression. It's called kernel regression. We're not going to focus on kernel regression since we kind of spent some time thinking about the density estimation version. We'll focus on something else called smoothing splines in a little bit more detail, just to give you a little bit of variety. Equally important announcement I wanted to make, other than the homework you do on Friday, is that when I give lectures from now on, so next week, I'm going to, halfway through we'll take like a 5-minute break, but in that 5 minutes, I'm going to tell a joke about statistics and machine learning. And what's going to happen is, I'll tell the first joke on, Monday, and then every lecture after that, I'm going to tell a joke from anybody wants to send me a joke via email, I'll tell that joke. And, I'll screen it obviously, it has to be PG, and it has to be about statistics and machine learning. But we'll keep like a running winner, so I'm sure my joke will be beaten the first.
And there's bonus marks for the best joke.
Yeah, that's right. Actually, I think what we'll do is the joke that runs the most number of classes in a row, we'll kind of assign some kind of award at the end for that person. All right, so I'll just set us up, like I said, for non-parametric regression. Okay, so I should also mention there's kind of an interesting tie between density estimation and non-parametric regression, wherein we can actually use the kernel density estimate to give us a regression estimator. And almost all of the methods I talked about, we can also form density estimates from them by normalizing them in a way. So we won't really go in detail about that latter point, but alternatives for density estimation come from these non-parametric estimators. So you can just kind of keep that in mind. So the setup is that we're just going to start with some pair of random variables, x and y. So in density estimation, we only had x. Now we have a y to go along with it. And to stick with various notation, I'll denote the dimension of the input space as d. So these are our inputs, our features, our predictors, they're in RD. These are our outputs, or our outcomes, or our responses. They're just real values in non-parametric regression. And the goal really is to estimate this regression function. So it's the conditional expectation of y given that our predictor variable x is equal to some specified value little x. So what we really want to do is estimate this regression function. Now, the usual setup, right, is that we have, we'll think about having n IID samples. So these guys have the same joint distribution as capital X and Y. And I hope it's not confusing notation, but I don't mean that these are fixed. These are also random. They're just samples from the same joint distribution. But I'll just use in the convention that when I talk about doing things with data, I'll use little case stuff. When I talk about population variables, I'll use uppercase letters. Right, so these are IID samples from the same joint distribution as those guys. And right, so the goal is to, from these guys, I'm going to construct some estimate f out of f0. And we'll look at like tons of ways to construct that estimate f hat. And so what's the basic way of kind of expressing these samples via an error model? Well, I can write it like this. I can write yi equals f0 of xi plus error, where I claim that these errors, they're IID, and they have mean 0. So let me ask something. When I've written down this model here, have I made any additional assumptions? Have I lost any kind of amount of generality writing this down? How many people think that this is like some kind of a stronger assumption than just saying that I have IID samples from a joint distribution, this error model? This is stronger. Okay, how many people think it's the same? There's nothing I did differently here. So we have an overwhelming 3-to-1 count of people who think that it's the same. Yeah, it is the same. There's nothing here that I've done that's assuming more. I'm not cheating in any way. Let's just define these errors to be yi minus f of xi. Right, that's what makes that equation true. And these are IID because the pair is xi, yi are IID. So there's no reason why epsilon I would be dependent with epsilon j. They're defined in terms of IID samples. And let's take the expectation of them. If I take their expectation, I get the expected value of yi minus the expected value of f mod of xi. But look, f mod of xi was the conditional expectation of yi given xi. Right? So I take two expectations. It's an iterated expectation. It's just 0. It's the expected value of yi minus the expected value of the expected value of yi conditional on xi. Right? So that's just 0. So actually this model here where I said I have these IID errors with 0 expectation, this is completely general. It's just like saying I observe IID samples. So this is the one that we'll kind of always keep in mind. Alright, so I'm going to call this the weak model assumption. Because like I said, it's very general. We could ask for a little more, and there's nothing really wrong with that, except we should just be aware of the fact that it is stronger. So what I'll call the strong model assumption we set up for non-chromatic regression is the following. So it'll be the same as above. So I'll assume that model, but I'm going to assume something else, which is that I'm going to assume that each epsilon I is independent of each xi. I forgot to mention that I will post lecture notes just like Larry did for all of this stuff, and it'll contain this information. So if you just are wanting to listen now, it's fine not to copy this now. I'll post them by Monday. All right. So why is this so much stronger than this one? Does somebody have a guess for why maybe we think this? Maybe it's an unreasonable assumption in practice, for example, to make in certain situations. and the distribution of the errors shouldn't depend on the distribution of the inputs. Statisticians sometimes will balk at this. Probably Larry is throwing up a bit in his mouth thinking about this assumption. I know Larry doesn't like to make kind of these strong assumptions all the time when he's writing papers or books. So the reason is, let's think about in practice, what happens if we actually assumed a model that was of the form of this guy with independent errors. Errors are independent of the inputs, but the true model actually depended on some other variables that we didn't measure. So let's suppose actually it was the case that y was f naught of xi plus, we'll call it g naught of zi plus epsilon I prime. Okay? And we can even further suppose that this model is appropriately specified and that these errors are independent of the inputs, so xi and zi. Well then, in assuming that form, we're actually treating this as the error, right? This is acting as the error. And so if there's any kind of dependence between z and x, if there's any correlation between z and x, then we're in trouble, because this error is not independent of x. So in other words, in a misspecified model, the errors are not going to be independent of the inputs, right? Because the errors are actually going to contain some other variable that may be correlated with our input points that also drives the response. So in practice, you would almost never believe that the model you've written down to then fit it. A regression estimate or something is actually the right one, because there are almost always other variables that you are not taking into account that also kind of drive the response to these things. All right, so that's why that one's a lot stronger. All right, just a word. I guess another common thing to do is to say x isn't random, x is fixed. So we'll just assume I have a bunch of fixed inputs, and they're arbitrary, and we'll just treat the problem that way. Well, that's actually really the same as starting with this model and just conditioning on x. And if we assume the strong model assumption that the epsilon I are independent of x, then by conditioning on x, it doesn't change the distribution of the errors. So actually, it's really identical to this model, conditioning on x. Okay, so random x or fixed x, they're really the same as long as we assume that the inputs are independent of the errors. And operationally, none of the methods that we'll talk about, most of them it doesn't really matter whether you treat the input points as fixed or random, so we won't make this distinction from here on out when it comes to discussing the methods. When it comes to theory, sometimes it's actually easier to assume fixed x versus random x. And so I will make it clear whether I'm talking about the inputs being fixed or random. In particular, if we happen to look at the x's being not fixed and arbitrary, but fixed and evenly spaced, like in this very simple one-dimensional setup, if the inputs are just evenly spaced over 0, 1, then some methods actually are designed for this very special case. So the primary example being wavelets. Wavelets, in their kind of most fundamental definition, depend on this very heavily, this assumption. And also theory sometimes can be made a lot clearer in this case. So I'll just be careful letting you know kind of what world we're living in, but if I don't say anything when we're talking about the methods, just remember that it doesn't really matter operationally for most methods. Fixed or random, it really boils down to the same thing when we define the method. So we're gonna start off with kind of the straw man that we can, oh yeah, question.
When you assume that tuple xy is IID, does that mean that fixed i's are IID?
I assume that the pairs x, I, y, are IID.
So
Yeah.
does that also imply that x itself is IID, different x like x and x?
Well, yeah, I mean, I can't have, right, if the pair xi, yi is independent of the pair xi, yj, then I can't have dependence between the x's.
Yes, so if they are independent, then any hidden variable zi is going to be independent of all the other xi, because xi itself are independent.
I didn't say that zi and an xi are independent. So xi is not independent of yi, right? Certainly not. I mean, this is, I can think about yi being generated from this model. I can think about, for example, only the x's and the errors being random, and y that comes from this model. Does that make sense? Any other questions? Okay, so the first method we'll talk about, it's a pretty simple one. Kind of reminds me a bit of the histogram estimator, although that may just be me in density estimation. And it's a natural place to start. And since we only have a few minutes left, I'll just introduce it, and then we'll just kind of chat a bit about its properties informally. Next time we might discuss it in a little more detail, and then we'll quickly move on to other estimators. All right, so the first one is KNN, so K nearest neighbors. Regression. And so, okay, from this, right, from this sample, x1, y1 to xn, yn, I just estimate this function f hat. You give me any input point x, I'll return to you the following fitted value. I'll just take, for a fixed integer k, so positive, just fix it for now, it's tuning parameters like the bandwidth was in kernel regression. I'll take an average over, I'm going to write this for the set of indices, so 1 through n, that correspond to the k closest points to my input point. I'll take their yi values and I'll just average them. That's k nearest neighbors. So nk of any point x, it's the set of k indices close such that xi is one of the k closest points to x. Okay, another way of writing this, which is going to help when we study these things next time, is just actually a weighted average of the yi points. It's kind of trivial to make this representation. Where now the w's, I'm going to say at a given point x, it's just either going to be 1 over k or 0. And it's just 1 over k if xi is, one of x's k closest neighbors. And 0 otherwise. So you guys have seen this in 701, right? Or in other classes? Not yet? Yeah. All right, so I think we're pretty much, we are over time. Okay, so this is k nearest neighbors. It's kind of like the straw man. We just start off with this non-parametric regression. The biggest downfall that we can see kind of apparently is that it's not smooth. So as a function of x, it doesn't behave smoothly. And you can see that directly because these weights aren't smooth. They're just 1 over k or 0. So kind of like the histogram estimator, it eventually wasn't smooth. Okay, so we'll talk about the properties a little next time, but just think about, we're going to basically go for a smooth analog of this as our first step. So I guess we'll see you on Monday, and remember the